Hello and welcome. This video is one of two videos on section 5.4. In this video, we're going to practice calculating integrals of the form integral a to b of f of x dx and just the integral of f of x dx. So these are two objects that look pretty similar, and the way we say them is pretty similar. We both call them integrals, but they mean very, very different things. So this first thing with the AB, fx dx, this represents an area. And the way mathematicians distinguish this is they use the word definite. So this is a definite integral. Definite integral. And the second one on the right-hand side here represents an antiderivative. Antiderivative, if you remember from a previous video, is just the function that when I differentiate it, I end up with f of x, right? And this is called indefinite. Those are just, adjectives. You don't have to go deeper into the meanings of them, but I really do need you to remember that the definite version with the a and the b always represents an area, which is a number. The area is 17. The second one with no AB represents an antiderivative. So the answer is a function. The antiderivative is x squared plus sine x, right? It is a function. So they're very, very different critters. The fundamental theorem of calculus connects these two things, saying that, oh yeah, we can calculate a area, a definite integral, by using the antiderivative, an indefinite integral, right? So they are connected, but calculating them, well, we're going to practice that today. So doing integrals of whatever version is not as easy as doing derivatives. Most people will agree. I think everyone agrees with that. There are sort of general rules for doing derivatives. If I recognize this type of function, I do this kind of thing. There's a product rule, there's a chain rule, etc. They're not really those kinds of things for antiderivatives. Pretty much, we have a list of antiderivative formulas. If you have one of those things, we use the formula. If you don't have one of those things, you need to algebraically simplify what you have until it looks like one of those things. All right, that sounds a little vague, so let me be more specific with an example. So let's look at this example A down here, where I have the integral. This is the indefinite integral of the square root of x dx. So if I go to a list of formulas for integrals, for example, the one I have available on our Canvas page, there are many of them. I didn't write down all of them because there are lots and lots of them. I wrote down 32 of them that are pretty common and some general ideas down below. But if you scan even this list of integrals that I provided, you won't find the antiderivative of the square root of x. It's just not there. It's not one of the common integral formulas. So the idea would be to simplify this square root of x into something which is on the list. Now, we've talked about this before, so you may remember this. In calculus, it's very difficult to work with square roots and other kinds of radicals. And so we simplify them into fractional exponents to make them much easier to simplify and work with. So the square root is going to be written as the 1/2 exponent. And x to the 1/2 is x to a number. That is a recognizable derivative formula. Is it a recognizable antiderivative formula? So we go to our integral formulas, and in fact, it's number 2. The antiderivative of x to a number is given by this, x to the number plus 1 over the number plus 1 plus c. So here's an example where, in one step, we're able to get it to a recognizable formula. And this is something you probably already have used before in previous practice problems where we're talking about antiderivatives. All right, so we know this is going to equal x to the n plus 1. 1/2 plus 1 is 3/2, divided by 3/2, plus a constant. And we want to simplify this, so we'll write this divided by 3/2 as 2/3. So 2/3 x to the 3/2 plus c. is the function that is, when I differentiate it, I get square root of x. And of course, you can verify that, right? You can even grade your own integral problems. You can just verify by finding the derivative of the thing you just found, 2/3 x to the 3/2 plus c. And you better get the original function, square root of x, otherwise your answer is incorrect. So the derivative of 2/3 as a constant multiple does not affect the derivative. The derivative of x to the 3/2 is 3/2 x to the one smaller exponent. One smaller than 3/2 is 1/2. And the derivative of plus c is plus 0. You can see that the numbers divide out, leaving just 1 x to the 1/2, which, as we know, is the same thing as square root of x. So, of course, you can verify your antiderivative problems, your integral problems, just by redifferentiating them. Anyway, so that's an example of an indefinite integral where we found the antiderivative of the given function. We're going to do a similar problem. It's the same type of function, but we have a definite integral with a 4 and a 9 here. So this is going to represent an area. If you want to have a visual idea, we have the square root of x, which is sort of like a function like this. This is y equals square root of x. And we have some x values. These numbers here represent x values. So we have somewhere x equals 4 and x equals 9. And if we connect those x values up to the function, the signed area here, which apparently is positive because it's all above the x-axis, that area represents our integral. So the 4 and the 9 are x values. I oftentimes will write this emphasizing this here. But mathematicians typically don't do this. They just write the 4 and the 9. They say, oh, you figured it out. You know what it's the x-axis. I think for most people, they remember it's the x's. But as you'll see in section 5.5, when we start doing some much more complicated algebra simplifications, sometimes it's helpful to have a reminder because we're going to be changing x's to a different variable, and the 4 and the 9 will not be the new variable, it's the old variable, and it just gets confusing if you have any difficulty keeping track of all the different letters. Anyway, so the fundamental theorem of calculus says that we can find this area by doing the antiderivative and substituting the two endpoint numbers. So we know from the previous problem, so from here, from A, we get an answer of 2/3 x to the 3/2 plus c. But that is the antiderivative. To find the definite integral, we have to plug in the two values of 4 and 9. And the way we oftentimes write this is we say we're going to plug in x equals 4 and x equals 9. And this bar, you may remember, sometimes they put like a little flag on here. This bar means evaluate at. And when you put the two numbers, 9 and 4, it means not only you're going to evaluate it at those two numbers, 9 and 4, but you're going to subtract. All right, so I'll finish off this problem. If I can get some more space, here we go. So I'm going to plug in the top number first. Plus c, that's the x equals 9 version. And then I'm going to plug in the x equals 4 version. And work out the numbers. So 9 to the 3/2 you can do on a calculator, or you can do by hand. The square root of 9 is 3, and 3 cubed is 27. So this is 27. And here, 4 to 3/2, the square root of 4 is 2. 2 cubed is 8. So this is minus 2/3 times 8. And then I also have a minus c because I have a minus both of these guys, right? Remember the distributive property. All right, and as always with these definite integrals, The plus c will be accompanied with a minus c, which will add to 0. So a lot of people neglect the c after a while just because it becomes redundant that the c's always add to 0. So 2/3 times 27, I'll just write this as 54 thirds. And 2/3 times 8, I'll just write this as 16 thirds. And 54 thirds minus 16 thirds. Well, let's see, 54 minus 14 is 40. So this is a little bit less than 40. So something like 38 thirds. And that's the area. So the area here, that's the area, right? If you have 4 and 9, and of course the y value here is 2 and the y value here is 3. How do I know this? Because I know the formula. Square root of 4 is 2, square root of 9 is 3. So if you have that little, sort of box-like thing, it's not really box, but it's like a curved top part. That area is 38 thirds, square inches or square feet, whatever the axes are measured in. All right, so that is the definite integral as opposed to the indefinite integral. So that's just our warm-up problems. We'll start getting a little more complicated. I'm going to be focusing more on the indefinite integrals. So that's the ones that look like this, because the definite integrals is basically the same thing. You do the indefinite integral first, and then you plug in some numbers, and it becomes an arithmetic problem. So anytime you have a definite integral, you really have to do the indefinite integral first, and then plug in some numbers and subtract. So I'm going to be focusing for the rest of this video on the indefinite integral part and less on the actual plugging in numbers and doing the arithmetic. All right, so here's my next example, which is a C here. Maybe a little bit bigger. Okay, so I have this thing right here. So 2x minus 5 squared. We have in the derivative world a sort of chain rule for this. There's no such thing as a chain rule in antiderivatives. Once again, it's recognizable or it needs to be simplified algebraically. So what's recognizable? Well, I would recommend just using this formula sheet and seeing, is there anything that looks like, a parentheses of stuff being squared, or to any exponent for that matter. And you can go through this and you'll find out that there is none of them. So it's not a recognizable formula. I really recommend having this formula literally printed out and next to you. Like flipping between tabs is way less efficient than actually having a piece of paper next to you, and you can just look at your paper and look at the problem and say, do I recognize this as one of the formulas? Yes or no, and then you can proceed from there. So how do we simplify 2x minus 5 being squared? Well, one of the ways that may sort of come to you is that we can distribute. We can multiply this out because we've multiplied things being squared before. So this is 2x minus 5 times itself. This becomes, I'll write the whole thing. You can do the FOIL thing if you want. I'm going to skip a step with the middle terms and just say this is what it is. Officially, this is all the stuff times dx, but it looks confusing, and so I'm going to sort of leave off the parentheses. I hope you realize it's just this whole thing times dx. And then I'm just not writing this to make it clear when I'm explaining things. So it's this critter that I'm trying to find the antiderivative of. The dx appears to not really have a meaning. Like, why do we even need a dx there? There's a couple of reasons why we definitely need to have the dx there. And one of the main things would be in our next section, 5.5, you'll see that the dx is imperative in order for us to find antiderivatives. So have a little patience. You also may remember that this all comes from the idea of length times width. We had some function. We have a height, which is f of x, and we have a width, which is dx, and we're multiplying these to find the area. That's where this all came from, the dx thing. But as I said, it has many more important uses than just the historical version of calculating areas. All right, with all that preamble, let's just do some antiderivatives. Our is this thing recognizable? Well, we do know for antiderivatives that are separated by plus signs and minus signs, we can do each of these separately, right? So that's the sum rule or the difference rule for antiderivatives. So we can antidifferentiate each of these. 4x squared is one of our functions that we can antidifferentiate it. We used it for the x to the 1/2. It's this number 2 right here. And 20x is another polynomial. 25 is just a constant. And for the constant, that's also one of our formulas right here, number 1, the integral of a constant. Or you can just kind of backwards think about what the answer would be, because we know that the derivative of a linear function is a constant. So at this point, it's all recognizable. So we can go ahead and do this. The multiplying of a constant does not affect derivatives or antiderivatives. So we get x to the 3 over 3 for the derivative of that thing. We get x to the 2 over 2 for this thing. And we get x for our constant. And then we get our plus c. Don't forget the plus c. You'll be sad that you lose a point on each question where you forget the plus c. So remember that, please. Let's write this in a simplified format. So we get 4/3 x cubed, and that's minus 10 x squared. And then we get plus 25x plus c. And that is the simplified answer for the integral of 2x minus 5 all being squared. Okay. D, what do we do with D? Well, again, we have a sum of things, so we can do each of these separately. Do I recognize x cubed? Yeah, that's one I just used. Is 3 to the x one of my recognizable formulas? In fact, it is. It's right here, number 4. N to the x, n and c are constants. So anytime you see an n or a c, it's going to represent just a physical number. So n to the x could be any number raised to the x, in this case, 3 to the x. So we have a formula for any number raised to the x power. And the other part of our integral problem is a sine x. And you may even know what the antiderivative of sine x is, but yes, it is on the formula right here on the formula sheet. The antiderivative of sine x is negative cosine x plus c. All right, so we're going to get the antiderivative of x cubed. Do this in green, I guess. So that's x to the 4th over 4. The antiderivative of 3 to the x is 3 to the x divided by ln of 3. That's supposed to say ln. It doesn't look like ln. Ooh. There we go. And that's the formula over here. Again, have those formula sheets. Oops, not Desmos. Okay, I think. Yeah, I think. Okay, hold on one second. Yeah, I accidentally closed my tab, so I got it back here. Sine x is one of our formulas right here. And we're going to go ahead and write out that. Oh, I was doing 3 to the x over ln 3. Yeah. I was just double checking with you that if I have a number to the x, the antiderivative is number to the x over the natural log of n plus c. Sorry for the messy video. Anyway, so that's that formula for the antiderivative of 3 to the x. The antiderivative of sine x, according to the formula sheet, or if you remember your derivative formulas, it's a minus cosine x, and we do get the plus c. Now, some students say, well, don't we get a plus c for each of these? Don't we get a plus c for this one, a plus c for this one, and a plus c for this one? Now, you really do, actually, and they are different constants. So maybe we should call this C1 and C2 and C3, right? Because they don't have to be the same constant when you're anti-differentiating x to the 3rd and when you're anti-differentiating 3 to the x, etc. So you really end up with 3 constants here, but we'll just call C the combination of C1 plus C2 plus C3. So we don't really need 3 constants. We can add them to be another constant, right? So we don't need to write 3 separate constants, and we never need to solve for each individual constant. We just need to solve for the 3 constants altogether if we need to solve for it at all. So there's no reason to write all kinds of separate little constants. Just write one constant to rule them all, I guess. Okay, so that is our answer for D. There's nothing really to simplify here. It's just an opportunity for me to talk about some of the little, subtleties about antidifferentiation. All right. So next question, we have a product of two things, x minus 2, x minus 3. There is no product rule for anti-differentiation for integrals. You can look through this list and you will not find a product rule. There's something you're going to learn in Calc 2 called integration by parts. It's not really a product rule. It's an algebraic simplification of a product of two functions. It's a pretty advanced algebraic technique. That's as close as we come. There is no product rule. So we have to simplify this. So what do we do? Well, once again, we can try, multiplying out distributing. So we would get something like, if I multiply x plus 2 times x minus 3, I would get x squared minus 3x plus 2x minus 6. And it's all, dx thing. And this is just if I combine like terms, this. And then I can anti-differentiate term by term. Antiderivative x squared is x cubed over 3. Antiderivative x is x squared over 2. Antiderivative minus 6 is minus 6x. I do get a constant because when I differentiate it, it goes to 0, so that has to be part of my antiderivative. And that would be the answer for example E. All right, we're just doing more examples. I think I got 4 or 5 more examples for you on this video. So we're just doing more videos. I'm doing different versions of simplification, different versions of trying to find the antiderivative. So that's what we're just practicing for the rest of this video. All right, so we got this one here. And remember, of course, you can pause at any time and give it a try, and then come back and see if you have gotten an answer that looks similar to the one I'm demonstrating. All right, so for F, we have 4 minus x squared on the top over here. Maybe I'll make this a little bit larger for people who have small screens. So 4 minus x squared, we can factor that. Remember, factoring 4 minus x squared can be written as 2 minus x, 2 plus x. It's a difference of squares. So we can imagine writing that sort of simplified version for our integral. The thing is that 2 minus x, 2 plus x, the multiplication of two things, isn't really part of our formula sheet, nor is the more complicated thing, which is the two things be multiplied divided by x. So you can skim through your formula sheet and you will not find anything looking like that. So the reason why I mention this is not because this actually works, but because not every time the simplification that first comes to you will be the one that actually helps, that works. So if factoring came to you and you tried it, I think that's fantastic. But you also have to sort of realize that every student who learns antiderivatives or doing these integration problems will not have their first intuition be correct every time. You have to every time saying, is this helping me? Is this getting to something that I recognize? Is this getting simpler? And if the answer is no, then you say, is there a different way I could try to simplify this so that I could have perhaps a better result? So that kind of checking yourself is imperative for doing these integral problems. So please check yourself. Okay, so what kind of other simplification is available? This is actually another distributive property problem, but distributive with a division instead of a multiplication. So you may recall that we've done this a few times before. We can divide each of these things by x. That is the distributive property. Oops, I forgot my integral sign. Oop. All right, and now I'm going to simplify these just a little bit. 4 over x, I'm going to leave the way it is. X squared over x is just x. and cosine x is just cosine x. All right, so is 4 over x recognizable? Well, it is if we don't include the 4. Now, 4 is a constant being multiplied or divided, doesn't matter, but it's a constant multiplication, and constants that are being multiplied don't affect derivatives. They don't affect antiderivatives. So when I go to my formula sheet and I look towards the top, I will see number 5, the antiderivative of 1 over x is written as the ln x. You may remember that from your derivative formulas. The derivative of ln x is 1 over x. This is the exact same thing in reverse because it's an antiderivative versus a derivative. And the 4 will not affect the derivative nor the antiderivative. It just gets carried forth. So the antiderivative of 4 over x would be 4 times the antiderivative of 1 over x, which is just 4 times ln of x. And the derivative of x is x squared over 2. And the derivative of the antiderivative of cosine x is sine x. And then we get our favorite plus c at the end. And if you're unfamiliar, if you don't remember what the antiderivative of cosine x is, it's fantastic. Great idea just to go to your formula sheet and say, oh, okay, number 8, antiderivative of cosine is just sine, right? So again, don't be afraid to have a formula sheet next to you or available to help you do these recognizable antiderivatives. All right, last page. All right, so here we have a trig integral. Integral of pi times tangent times secant times cosecant. Fun, if you consider that kind of thing fun. So is this a formula? Well, I probably won't shock you by saying it's not. So if we look here, there's no multiplication. There's lots of trig things: antiderivative of tangent, antiderivative of cotangent, antiderivative of cosecant, antiderivative of cosecant squared. Like we can antidifferentiate the squares. That's a formula, right? There's lots of these kinds of formulas here, but no product of trig functions. So what can we do? Well, yes, we simplify this. So we're going to write this out as, well, to simplify trig stuff, if you remember from your pre-calculus, one of the ways we do it is convert everything into sines and cosines. So tangent, if you go to your trig formula sheet, which I didn't post here, but you can look it up. Tangent is sine over cosine. It's the, the y over x kind of thing. A secant is 1 over cosine. Oops, this is times. And cosecant is 1 over sine. Many of you remember these, but if you don't, just look them up on your trig formula sheet. I do have a trig formula sheet available on Canvas. I have a bunch of different formula sheets. Exponent and log formulas, trig formulas, derivative formulas, antiderivative formulas. So the trig formulas is where you would find that one. Okay, let's see. So we have some division or cancellation, as a lot of people would like to say. Oh, I forgot my dx. Uh-oh. There, dx comes down. So the signs divide out. I have a cosine and a cosine. And so I get a pi times 1 over cosine x squared. And then we get our dx times dx. Now, pi is a constant, 3.14, etc. Constants, when they're being multiplied, do not affect derivatives or antiderivatives. So a lot of people will just write the pi as a multiplication after they do the antiderivative. So they'll even write the pi on the outside of the integral symbol, just so they can focus on the fact that I don't need to worry about the pi. I'm just going to worry about the cosine thing, the function inside. All right, so what we're looking for is 1 over cosine x being squared on our formula sheet. And unfortunately, there's no 1 over anything here. I guess there's 1 over 1 squared of x, 1 minus x squared kind of thing, but there's no 1 over the trig thing anywhere in our formula sheet. So we need to do more simplification. If you don't find it here, we need to either start again at the beginning and try a different type of simplification or simplify some more. So here's where it helps if you remember some of your trig formulas, or if you have your trig formula sheet next to you, handy next to you. The 1 over cosine is the same as secant. In fact, we did it over here. Secant is 1 over cosine. We're just doing the same thing backwards, going in reverse. So we get pi 1 over cosine squared would be secant squared. Move over here, perhaps. And for many folks, this will look like it's not getting better at all. Like secant is much more complicated than cosine, at least in most people's opinions. However, remember, we are trying to match up with our formula sheet, and lo and behold, there is a formula for secant x squared. So I highly recommend that you have this printed out in front of you so that you're not just constantly wondering if something is on the sheet. You can look at it directly and say, hey, secant squared is one of my formulas, and that integral antiderivative is just tangent x. And that may sound familiar because if you have done the derivative of tangent x, you may have memorized or you may remember that the derivative of tangent x is in fact secant squared. All right, so now we have simplified it to the point where it's recognizable. And this again is the challenge on every of these integral problems. Try to get it to the point where it's recognizable. The pi just hangs out. The antiderivative of secant squared is tangent. And then, of course, we get our constant added on from the antiderivative. So that's the antiderivative answer for part G. All right. If you haven't already considered it, haven't already been doing so, again, I recommend you pause and try letter H. See if you can come up with the antiderivative before you watch my solution. All right, so hopefully you gave that a try. So now I'm going to write out my solution for H. I have cotangent squared over cosine squared. I'm going to be simplifying this. Maybe I'll try the same technique as before. Cotangent is cosine over sine. And because it's squared, I'm going to have each of these squared. So cosine squared over sine squared. And on the bottom, we have cosine squared. Now, some of you who are very, sort of expert at algebra may recognize immediately how these can be simplified, but I'm going to do a couple steps in between for folks who are less confident on their algebra simplification. So we have a fraction divided by this cosine squared x. So I'm going to write this as the fraction. I guess I should be keeping my integral, right? People are going to complain that I don't have my integral sign there. All right, so I'm just simplifying the inside stuff. So I have cosine squared over sine squared divided by the bottom thing, cosine squared, and dx. And once again, this is all times dx, and I'm leaving off the times thing just to make it easier for me to explain things. Okay. So if I divide by something, that's the same as multiplying by the reciprocal. So I can imagine this over 1, and I get my first thing. Instead of divided by this fraction, I get times the reciprocal of this fraction. So 1 over cosine squared. And so now you may begin to see how it simplifies, because the cosine squared has something on the top and something on the bottom. And we're left with 1 over sine squared. So I'll write this up here. And if you remember our trick from the previous problem, There's no antiderivative formulas for fractions of trig things. However, 1 over sine does have a trigonometric formula for. 1 over sine is the same as cosecant. So I can write this as cosecant squared x dx. And cosecant squared does have a formula on our formula sheet. It's right here, number 14. Antiderivative of cosine squared is negative cotangent plus our integration constant, which again is basically the backwards of a derivative formula that you've used before. So this is negative cotangent of x plus c. And that is the antiderivative of this crazy fraction in letter H. All right, a few more practice problems, or maybe one more. So we're going to do this letter I. Again, great time to pause and try this before I write out the solution. All right, so here's my solution to this I example. We have some constants. 6 is a constant, 7 is a constant. They're both being multiplied or divided, same thing in math. So the first thing that you might want to think about is that the 6 and the 7 will not affect the antiderivative. And in fact, a lot of people will just write the 6 and the 7 outside of the antiderivative symbol. So it's 6 over 7 times this antiderivative. We end up with a 1 on the top, and we end up with this cube root thing. I'm going to write this using fractional exponents because, of course, math prefers fractional exponents as opposed to these radical things. I get an exponent of 5 and an exponent of 1/3. That makes an exponent of 5/3. And that's a 5. All right, I'll write this again. Exponent of 5/3. And then I get the dx over here. I still don't like the way that looks. All right, I'm going to give it one more try. Legibility is important in math because all the little details are so important. All right, so this we have as our, sort of cleaned up version of this, writing it as a fractional exponent as opposed to a radical, and moving those numbers outside the antiderivative symbol to make it easier to spot. We don't have a formula for 1 over x to a number, but we do have a formula for x to a number. So you'll have to go back to your algebra skills, your pre-calculus skills, and say, hey, I can use negative exponents to represent this thing. This would be x to the negative 5/3. We have done this before in doing derivatives. We do the same kind of algebra simplification for antiderivatives. All right, so this is x to a number. X to the number we use many times. That's one of our very first formulas here, number 2, in fact. X to a number is x to the number plus 1 over the number plus 1 plus our integration constant. So we get our 6/7, and we do one number bigger than this. Negative 5/3 plus 1 is negative 5/3 plus 3/3, which is negative 2/3. So we x to the negative 2/3, and then we divide by negative 2/3. That's x to the n plus 1 divided by n plus 1. And then we get our plus c at the end. We will need to simplify this, just combining things together, making it look not so messy. So I'm going to, instead of divide by this, I'm going to multiply by the reciprocal. And I can combine these together. Some people will like divide before they multiply, or you can multiply and then simplify, or then divide. It comes out the same way. But however you want to do this, it ends up with negative 9/7 x to the negative 2/3 plus our integration constant. And that is the antiderivative of this example here. All right, well, that's it for today's video. Hopefully this was helpful, and you will reach out if you have any additional questions. And I hope you have an enjoyable day.